Hello everyone. Hello everyone at the fourth day of the Kumquat Conference. Today we're joining a theoretical physics session, a second theoretical physics session. And welcome to everyone that is joining in on YouTube and Twitch. And welcome to all participants. Now we will start with Himanshu Dadi about transport properties of Manganite-based heterostructure. If you are ready, you can share your screen, and the floor is yours.
Yes, sure, sir. Am I audible?
Yes, we can hear you. I think the talk has to, yes, sharing is disabled.
I hope my screen is visible.
Yes, we can. Yes, we can see your screen.
Good afternoon and good evening, everyone. I am Himanshu Dadi, a research scholar from India who is pursuing her PhD under the guidance of Dr. Piyush Solanki. And the title of my today's talk is Transport Properties of Manganite-based Heterostructures. So these are my team members, and this is my abstract, which you have read in the abstract book. So what will be the plan of today's talk will be, like first I will introduce to the manganites and multiferrite materials, that what are those, then what are the various synthesis method available, and which technique did I use and why did I use it, what are the characterizations which I have performed, and their results and discussions. So first of all, introduction to manganites and multiferrites. So manganites are materials named after the main element manganese, because manganese is the material which provides us mixed valence state in these materials, leading to various interesting properties. The general formula for manganites is R1 minus AX Mn(3), where R is the rare earth ion, A is a divalent ion, alkaline earth ion, which we are doping, which is generally divalent, but it can be monovalent, trivalent, tetravalent also. This is manganese, which plays an important role because depending upon the doping concentration of the rare earth ion, that is in place of rare earth ion, how many alkaline or whichever material we are doping, according to that, the valency of the manganese ion changes. So why did we want to study the manganites? Because there are various salient features, like there are 4 degrees of freedom: charge, orbital, lattice, and spin. They are intrinsically inhomogeneous patterns of manganite. Means that within the manganites, you will observe various kind of structures which are not possible in variety of materials. And colossal magnetic resistance, that is, on application of small amount of magnetic field, we will observe a huge change in the resistance of resistance. Then multiferroids. First of all, what are multiferroids? Multiferroids means those materials which exhibit multiple ferric properties like ferroelectricity, ferromagnetism, ferroelasticity, all together are known as multiferroids. So if we combine the charge, if there is changes in charge occurring on application of electric field, then those materials are known as ferroelectric materials. And if on application of magnetic field, various changes in spins are observed, those are known as magnetic multiferrite materials. If we can combine both of these, then we will get extraordinary materials which are useful for memory and sensor applications. So what are the, I have synthesized thin films. So what are the various techniques available for the synthesis of thin films? These are pulsed laser deposition, chemical solution deposition, chemical vapor deposition, molecular beam epitaxy, and sputtering, which can be carried out by DC source as well as RF source. So on the right, you can see a schematic of what happens during a pulsed laser deposition. So during a pulsed laser deposition method, a laser pulse is being passed and it hits the target material, which is what we want to deposit as a thin film on our substrate. On application of this laser, the molecules from the surface, atoms and molecules from the surface start to evaporate and form a plasma plume. Within the same chamber, a substrate is placed at the 45-degree angle. So when these molecules evaporate, they go and deposit on the substrate, forming an epitaxial thin film. What are the precautions needed here are that this whole chamber should be vacuum packed and the vacuum should be very high, around 10⁻⁵ torr. Then we need very high energy pulse, and the chambers sometimes need to be filled either with an inert gas or with oxygen gas. So in order to prevent the oxide materials from losing their stoichiometry. Then chemical solution deposition. This is the technique which I have used and I will discuss further in detail. Chemical vapor deposition. In chemical vapor deposition, a solution is being formed and that solution is then being evaporated with the help of vapors. These vapors get deposited on the substrate and thus we obtain a thin film. So which technique did I use? I used chemical solution deposition technique, also known as CSD. Now the question is, why did I use this technique? First of all, it is a low cost technique. So you don't need hi-fi instruments to form thin films using this technique. It is a completely vacuum-free technique and can be carried out in normal environment by taking very minor precautions. Then the precursor solution which is formed can be formed from various starting materials like acetates, oxides, and nitrates, ferrites like this. And with this easy technique, even though this is a low cost and easily deposition technique, the output results which we get are very good. On the right, you can see the schematic of how deposition is being carried out. First of all, on a spin coating machine, the substrate is stuck to it using a dual sticky, and then a drop of the solution is placed. After running it, after spinning of the spin coater, the solution gets deposited throughout using centrifugation or centrifugal force, we can say. Then the substrate is heated, and on heating, we get the material, the thin film deposition. So as we can see, it is a really easy. And the thickness of the film can be easily controlled by using the molarity of the solution as well as the time of the deposition and RPMs of the spin coating. So what are the various characterization did I perform? First of all, to study the structural property, I have performed X-ray diffraction. And to study the transport and magnetotransport studies, I have taken resistivity versus temperature and resistivity versus magnetic field graphs. So this is the XRD graph. As here I can see, as here you can see, there are only 3 peaks visible. This is because the SRTiO3, that is STO substrate which I have used, is a single crystalline substrate having the orientation H00. And the one which I used has or had orientation 100, and general orientations are named as H00. After that, I had grown 100 nanometer thick LCMO layer over this. Because the LCMO layer grew within the same orientation as that of the substrate, we did not see any extra thing. And above that, I have grown LFO layer, that is LaFeO3, which is a multiferrite above the LCMO. It also grew in the same direction. So that's why we did, again, the same peak was modified instead of new peaks formed. So why did I select LaCaMnO3 with the stoichiometry 0.7.3? Because La 0.7, Ca 0.3 is the best stoichiometry which has been observed till date and gives us very good results whenever studied for these type of properties. And LaFeO3 and LCMO have cubic perovskite structure, which is having lattice parameters almost similar to that of SrTiO3, giving us the benefit that the strain of the system is very less. Then these are the resistivity versus temperature plot. So as you can see below, this is the schematic of a film and how have I performed the measurements. I have first applied the current across the channel, that is only on the LCMO layer, and measured the resistivity of the LCMO layer. So what happens is when the current flows through this, there are some within decrease in temperature, the insulating phase, which is prominent during the room temperature, starts to decrease. As the insulating phase starts to decrease and the metallic phase starts to increase, we can observe a decrease in resistivity. So from that, we obtain this type of curve. To understand it better, we can think it that on the left hand side, we can see this is a Mn3 plus and Mn4 plus ions are there. Because of the doping of Ca in the site of La, we obtain Mn3 plus and Mn4 plus valence state. And the hopping of charge carriers or electrons or spins is taking place through oxygen ion. So what happens is when the electron from Mn3 plus jumps towards the oxygen, at the same time the electron from the oxygen jumps to the Mn4 plus, leading to hopping of charge carriers, thus giving us conduction very well and the reduction in the resistance. On the right side, I have used percolation model to study and find out what is the transition temperature of these films at a particular magnetic field. So from this, I have found that with increase in magnetic field, the transition temperature shifts towards higher temperature and the resistivity decreases. Similar is the case with the interface, but what we have done during the interface is that on applying current through the channel, we have measured the resistivity across the interface. So what happens is now as the charge carriers try to cross the barrier across the interface, there is some kind of lattice mismatch. This lattice mismatch leads to difficulty in the transfer of ions from charges from LFO to LCMO, thus giving us higher resistivity as compared to that of the channel resistance, and thus we obtain a higher resistivity value. Similarly, percolation model was fit in this to understand the charge transport mechanism and to find the transition temperature, and it was found that in this same pattern follows. These are known as the Magneto resistance graph. That is, which is a very important property of manganite. That is Magneto resistance. So what happens is we measure the resistivity on application of magnetic field. From this graph, we can see that as we start to increase the magnetic field, the magneto resistance increases, and this property giving us around 65% of magneto resistance in negative, which is useful in spintronic devices. Thank you. If you have any questions, feel free to ask.
Thank you very much for your presentation. Now, are there any questions from the jury or from the participant? If not, then I would ask on the slide number 14, you showed us the results from the results and juxtaposed with fit, and
yes.
I was interested because the fit had this maximum for all the cases showcased here, but is there a reason why this why the results marked with symbols were not could not be
yeah, actually the symbols are the representation of the experimental measurements which we have got.
And my question is there a problem in experiments to increase the temperature so that the maximum can be seen in the experimental results?
No, there is not a problem, but it was a limitation of the system in which the measurements were carried out. So measurements could be carried out only up to a temperature of 320 Kelvin. So in order to find out the transition temperature, which in my case was higher as compared to that, I have used percolation model. So this percolation model gives us approximate idea of how higher the transition temperature can be. So the symbols were experimental results and the line was the fitting line.
Okay, thank you very much.
Welcome.
Okay, so now I think that we can proceed to the next speaker. And now we welcome Bartosz Grygielski from the Wrocław University of Science and Technology. And he will give us a presentation about Bayesian analysis of cosmic rays data for earthquake predictions. If you are ready, you can share your screen.
Okay, hello. Is everything visible?
Yes, everything is visible and you're loud and clear.
Okay, great. Then hello, welcome everyone. I would like to present to you data that we gathered along with Clementine Mostin, which is from the United Kingdom, and we worked on the project of Bayesian analysis of cosmic ray data for earthquake predictions under the tutelage of Dr. David Alvarez. During the particle physics summer student program. And first things first, what are the cosmic rays? They have various sources, just like you can see here, the sun, supernova remnants, magnetic fields, and when they come to the Earth and they interact with the atmosphere or various fields, they scatter. So we took the data from the Pierre Auger Observatory, which is located in Argentina, because it's a system of, well, so to say, small detectors that are spread around large area, so it's easier to actually determine from which so-called shower the detection call came.
Bartek, your mic is turned off.
Yeah, I figure. Sorry. So the thing that even started as to concern us was the Chile 2010 earthquake, because there was it was of a big magnitude. 8.8 is quite a strong one, and the unexpected anomaly was detected 20 days before. As we later realized, it's not perfect because it was measured from higher up. So the shift is actually 25 days, as we found out. And we came up with the correlation function, where we mapped the earthquake data and averaged it and divided by median. Averaged because the data is gathered in 5-day intervals, and they were averaged, but overall they were divided by their median, so that half of it is below 1 and half of it is over 1, which will come in handy in this correlation function. We did the same for the cosmic ray data, but we have measured the derivative because we're interested in the change in the flux, not in the signal itself. We also divided it by its own respective median and came up with the function which basically tells us when both of the signals are above their own medians or below, then it's positive, and when they are different flips, it is negative. And so you have it plotted here. This plot is, I believe, for a 15-day shift. And you can see at the histogram that there is an advantage of the positive results. And if it were completely random, then we would expect a uniform distribution. I mean, uniform above and below zero, obviously. And there is a study of the shift, which is a rough Gaussian distribution as well. But yeah, 25 days seemed to be the peak. But we also, if we wanted to determine it very precisely, we would have to consider that the data is gathered in the intervals, as I said. Then we come to the Bayesian analysis. I'm sure everyone knows the Bayes theorem, and the Bayesian probability gives us a posterior function, which is the probability. But the evidence is just a normalization factor. Likelihood is a function that tells us for the data we have gathered, which distribution is the most probable. You could say, I mean, if we get some data and we wanted to make a likelihood function, it would tell us for which standard deviation and median it's most probable that we get these results. And also it has a subjective factor that is pure, and it's based on our previous knowledge and measurements. So it's, as I said, subjective. Some may disagree that it's not that scientific, but it's there are ways to check if the confidence level of the functions that we get. And based on that, we wrote a function to find a change point in a signal. And so this was the signal that we checked if it was even working. Obviously, it's much harder to find where the signal changes in the usual scenario. But just to show you, our function, just like the delta function peaks, it made them in the points that the signal changed. It's mostly based on change in the standard deviation and mean, again, and worked well for the more complex signals as well. And yeah, we plotted now the whole data with change points, and we realized that the correlation function change points were closer to the earthquake data. So we concluded that it might have some impact. The magnitude of an earthquake could have an impact on the correlation that we get. Right, because our correlation function kind of is based on that. There is no limit to the value that we can get with it. And so we started to look at only energies above 0.4 exa-electron volts, with the shift, obviously, because we're working in that framework from now on. And roughly found that it doesn't really tell us that much. So we had to make another analysis. You could say it's already over, but it turned out that we actually could get something out of it. And so we took the earthquakes in the near proximity of the Pierre Auger Observatory. And only one didn't fit our predictions concerning the exponential dependability on the proportional earthquake energy, which is this value. Because, yeah, it's obviously, I mean, it seems to make sense, right, that near the detector, the earthquakes have less like other impacts, so the correlation could be visible more clearly there. And we ended up with the really nice fitted functions, which can help in predicting in the future other events. And we just narrowed it down to the to this interval. And when we did that and narrowed the both energy and time scale, we actually got really nice results. There is one point that wasn't clear what was it, but the ones that fit perfectly. So that was a really good sign that it could actually be working. Obviously, we have to remember that correlation doesn't mean causation. So obviously more research is needed, but we are happy with the results. And also we checked, it was a Fourier transform of the earthquake data and with the peaks. And when we have removed the fitting peaks from the signal, then we have gotten a nice downward linear trend. Very rough one, but if we could identify all of the peaks and the sources of these sources of the deviations from the linear downward trend, then we could possibly perfectly predict it. So that is our goal for the next few months or however long it takes. And I think it's very promising, but also it would need to be studied more widely across the world and more quantitatively, because it is obviously just one case, but it's also a very well-fitting case. So I think that's promising. And just to, if anyone wanted to help us and science in general, my tutor would have killed me if I didn't mention the Credo project. I have a minute left, so it's basically trying to make the system of detectors that we could carry in our pockets, because you can download an app that actually can detect the cosmic rays. And if we had it spread around across the whole world, then it would be much easier to well research the topic, and it could be really helpful in preventing maybe not preventing earthquake, but lowering the disaster that they bring. Thank you for attention. If these are the references that we have used, and if anyone has any questions, then
thank you very much. So I'll ask if there are any questions from the jury, or I see that.
I have one question.
Yes, go ahead, please.
yes.
So you have shown that your data shows that there's this correlation between those two events, I mean cosmic rays and earthquakes. So is there any idea of what is the mechanism of interaction here, of the connection between those two seemingly very different events? So maybe if there's no specific theory about that, can you at least speculate what would be the connection here?
I read up on that at the beginning because it seemed very strange indeed, and there isn't a clear one. There are various papers. If you contact me, I can send you some sources, but most of them are very obscure or rather naive. For example, like that the energy is gathered in the oceans and the Earth, and it just makes it somehow more mobile, but it seems like it would have a correlation with temperature as well, for example. So yeah, I think it's naive, and I think the most earthquakes occur on like March or April, so that doesn't really make sense. So answering, not really. There isn't one well-established correlation, but I mean cause. But yeah, we were working more on the correlations. But I'm also interested if it actually shows that there are multiple times shown that it works. Then yeah, definitely it's something to look at.
Thank you.
So, if possible, I would like to follow up to this question. Is it maybe possible that the correlation is between the process of detecting? So there is the fact that earthquakes can somehow interfere with the process of detecting the rays?
Interfere? Not really, because we have this 25-day shift. So the detection of rays also always precedes the earthquakes.
So are there any more questions, perhaps? If not, then thank you very much for your presentation.
Thank you.
And now our next speaker is Jakub Pawłowski, also from Wrocław University of Science and Technology. And he will give us a talk about non-commuting integrals of motion in the XXZ model.
Hello, everyone. Can I start right now?
Yes, go ahead.
Right, so I'll share my screen. Tell me, is it visible?
Yes, everything is in order.
All right, so as Arek told, my name is Jakub Pawłowski, and I'm a fourth-year undergrad student at Wrocław University of Science and Technology. And today I will talk to you about non-commuting integrals of motion in the XXZ model, and commuting integrals also, but we'll see. So let's start. I will begin the presentation by introducing you to the spin 1/2 model Hamiltonian. Then we'll try to motivate what we do, why these conserved quantities are important by introducing the spectral function. Later, we'll define more precisely what are the conserved quantities and more importantly, local conserved quantities. Then we'll proceed to some examples and once again, tell why they are important. And in the end, we'll break everything and by perturbing the Hamiltonian and see what happens. So let's start by the spin 1/2 XXZ model Hamiltonian. So we investigated on a one-dimensional lattice of L sides with periodic boundary conditions, and it looks like this. So it has this familiar form with this like kinetic term here with spin flips and the interaction between the nearest neighbors, and the S+ and S- operators are defined as usual, your spin lowering and raising operators, and the Sx, Sy, and Sz corresponds to the respective Pauli matrices multiplied by a constant. All right, so let's proceed to the spectral functions. And imagine that we want to learn something about the time evolution of an observable, so say A. So the first thing that comes to our mind is to study its autocorrelation function. However, autocorrelation functions are not very pleasant to work with. So we take their Fourier transform, obtaining so-called spectral functions. However, these spectral functions, it's usually quite prone to fluctuations. We would like to get rid of those fluctuations to smooth it out a bit. So therefore, we integrate it once again over like a finite frequency window. This gets rid of some of the fluctuations. And it is important to know that this omega here, it corresponds to the inverse time of the evolution of the observable. So the smaller this omega window here, the longer evolution times it corresponds to. So in this, it turns out that this can be described by such an equation, and these M and N states are the eigenstates of our Hamiltonian, and these are just the energies. And this is a general theory. It's not special to the XXZ Hamiltonian that I mentioned earlier. So we would like to know something about how this function behaves for very small omegas, that is very long times. And as it turned out that for this omega small in comparison with the system's energy scale, that means for the long enough times, we can approximate the spectral function as something proportional to the delta function, where this d0 is just the zero frequency limit of this integrated spectral function. That is just the sum of squares of modules of matrix elements over the same energies. So in case that we have a non-degenerate spectrum of Hamiltonian, this is just the diagonal part. So, but it's not very illuminating so far because, well, we just said that to study the limit of small omegas, we just need to take the limit with small omega. But as it turns out, this quantity D0, which is called stiffness, and for arbitrarily observable, it originates from its projection on the so-called local conserved quantities, which are the main topic of this talk. You can see that it can be calculated with certain equation. It's similar a bit to calculating the projection of a vector or on a subspace spanned by some set of vectors. So this is precisely the case here with these operators. And it's important to note that we have this equality here because we assume that we know all possible conserved quantities in our systems. What happens when we know only a subset of conserved quantities, that I will tell later about it. So we know where this D0 comes from, but where does this delta come from? This is very simple because our QAs are conserved quantities. This means that they commute with the Hamiltonian. That implies that the autocorrelation functions of them is constant, and while Fourier transform of constant is just proportional to the delta function. So this is why we have this delta here. All right, so we said why the local conserved quantities are important, but what are they exactly? So let's imagine an arbitrary Hamiltonian in the diagonal form, just like shown here. And from its form, we can see that there are many conserved quantities here. For example, all the projection operators on Hamiltonian eigenstates, because they're all commute with Hamiltonian. However, they cannot be expressed as a sum of local operators. They're highly non-local and in principle can span the whole system, whole lattice. But what means for the operator to be local? So imagine that this is our one-dimensional chain of spins, and we want to define an operator on it. So on this side, we just take an identity, another identity, and so on. And here we come to the part where we have something other than identities, for example, an S plus operator or a Z operator or something like that, but only on a finite sequence of sites in our chain. And this part is called the support of an operator. And in this case, we could say that this operator has support of M sites. Of course, when we investigate real operators, there are sums of such local operators. So for example, a full operator would be this one plus the one which is shifted by one side and shifted by another side, and so on and so forth. So you can sum it up by saying that local operators have finite support. They do not span the whole system. On the contrary, generic operator can have a support that spans the our whole system. Okay. So now let's look at some examples of local conserved quantities. The paradigmatic example of a local conserved quantity is the energy current. It's not only for Heisenberg model, but for concreteness, we will study this one here. It is defined via the suitable continuity equation, and it has the following form. It's seen that it has a support of 3 sides. So we got the I-1, I, and I+1 side, and translation over the whole system. What is also important to note about this operator, that these parts, they have the same number of S plus and S minus operators. That means that when we act with this operator on a state with fixed total Z component of the spin, we get back a state with the same spin. And that means that this operator commutes with the total SZ spin operator. This is why it's often called a commuting local conserved quantity. This is important, especially in numerical studies, because it allows us to restrict the studies to a subspace of full Hilbert space with fixed total spin or like fixed number of particles in the fermionic models. And this greatly reduces the computational complexity of our task. However, this time only for the delta equal to 1 in our Hamiltonian, which reduces to the so-called XXX model, there is another operator, the O1 operator, and it has the following form. It consists of just the S plus and S minus from Hermitian conjugate operators, and its consequence is its existence is a straightforward consequence of the SU2 symmetry of XXX model, which basically means that the spins are rotationally invariant. So we've got the obvious conserved quantity, which is the total z component of the spin. But because we can rotate the spins, that it means that the SX, total SX spin and total SY spin is also conserved. And from this, we can construct as a linear combinations this local conserved quantity. But there is a significant difference between this LCQ and the energy current, because it has only S plus and only S minus. So it means that if we were to act with this operator on a state with, say, total spin 0, we will get a linear combination with states with spin one higher and one lower. This means that this operator does not commute with the total SZ spin operator. So it's the titular non-commuting LCQ. And this makes our numerical studies much harder because we cannot restrict ourselves to a fixed spin subspace of the whole Hilbert space. In this case, we could, in principle, use the, say, total spin 0, total spin -1, total spin 1, and take the direct sum. But if I recall correctly, dimension of such direct sum would be greater than half of the dimension on the whole Hilbert space. So it wouldn't do much good for our numerical studies. All right, so now we know what are the LCQs, we know some examples. Now let's show another example why they are important. So we've got something that is called a Mazur bound for stiffness of a local observable. And this is the equality for calculating the stiffness of an observable that we showed before, but under the assumption that we do not know all local conserved quantities in our system, only a subset of them. So the equality turns into a lower bound for our stiffness. But why are local conserved quantities important and not all conserved quantities in general? As it turns out, this projection vanishes for non-local conserved quantities in the thermodynamic limit. So when you want to study properties of our system in thermodynamic limit, the non-local conserved quantities become irrelevant. But why is it important to have a lower bound for stiffness of an observable? So let's say that we want to study the spin transport on our lattice, and we start with initial spin density looking like that. It has a width of sigma, and we would like to know how it evolves in time, this width, this sigma. So in principle, the sigma can be constant. That means that spins are localized, but we don't want to talk about it in here. We can have the regular diffusive transport where the sigma is proportional to the square root of time. And we got the ballistic transport where sigma is just proportional to time. And as it turns out, this type of this transport is determined by the stiffness of spin current operator. When the stiffness is greater than 0, we have the ballistic transport in our system, and when it's 0, we've got just the diffusive transport. So if we could find local conserved quantities in our system of interest that the spin current operator has non-zero overlap with, we will have guaranteed that the spin transport in our system will be ballistic. Okay, so now we know about what are the local conserved quantities. We know some examples. We know why they are important. So now let's break everything and perturb the Hamiltonian. We do that by adding a next nearest neighbor interaction. So for arbitrary small parameter alpha, our Hamiltonian becomes non-integrable. This means that the conserved quantities, these local conserved quantities, cease to be conserved. The autocorrelation function decays with finite relaxation time, say tau alpha. We cannot say much about this decay in general, just as Dr. Riegel said in his presentations, but we can do some case studies. For example, imagine that these autocorrelation functions decays exponentially. This is, well, quite reasonable assumption, I think, because usually in physics, when there's decay, there's an exponential function lurking there somewhere. So if we were to assume that these autocorrelation functions decay exponentially, then the spectral function, which previously in the integrable model was just a delta function, this delta function would start to broaden. So it will become a Lorentzian, which is pretty well known because, well, this is the Fourier transform of exponential functions. But if we were to integrate this function again to obtain the integrated spectral function, we would get an arctangent function. And keep that in mind because we will see it in a moment. All right, so we want now to study the decay of the two examples of LCQ that I mentioned previously. So in order to do that, we will define the following quantity, this R as a function of omega and alpha. This is just the following quotient, that's the integrated spectral function divided by the infinite time limit of the integrated spectral functions. And in our case, this limit will be 1 for both LCQs, but it is important to include it because there are other quasi-local conserved quantities that for them this limit is not equal to 1. So this is a reminder what are those quantities, and now we will proceed to the plots. All right, so this is this function R as a function of omega, that is the frequency or inverse time. So the small omegas here, they correspond to the infinite time limit. So here we are actually taking the infinite time limit, and well, this picture is, well, underwhelming a bit. It doesn't say much apart from the obvious thing that in case of stronger perturbations, our LCQ decay more quickly. However, what we can do is scale these plots by dividing the frequency by the square of the perturbation. And now these curves collapse into one. And moreover, this one curve, it can be very well approximated by the arctangent function. So what we see here is that the energy current in our system, after turning on perturbation, which is given by interaction between nearest neighbors, it pretty much decays exponentially on the time scales given by this fitting parameter here. So we see that this assumption about exponential decay was in fact not unreasonable one. All right, so now let's do the same for the other local conserved quantities, that the one with S plus and S minus. And at first we see very, I guess, similar plot. So in principle, we could just, well, divide it by alpha squared and we'll be all set. But this is not the case. After scaling it by alpha square, we've got, well, nothing much better from the previous one. So the curves do not want to collapse into one. So this is not the case. We see that we don't have any arctangent here, and it's probably not an exponential decay. However, we can scale it by alpha instead of alpha square. And now we see that these curves collapse. So what we have witnessed here is that in the same system with the same perturbation and the same like order of magnitude perturbation strength, we get two very qualitatively different decays between different operators. And this is why it is very hard to say something in general about the decay of these quantities, because, well, it can differ from one LCQ to other LCQ in exactly same system. All right, so that's all I had for you today. So let's jump to the conclusions now. What we learned today is that we can learn a lot about time evolution of an observable from its spectral function. For long times, the spectral functions are encoded in projections of local conserved quantities. The existence of local conserved quantities can depend on the system's parameters. So, for example, the energy current exists for all values of delta, whereas the other non-commuting LCQ exists only for delta equal to 1. Perturbing the Hamiltonian away from integrability causes the LCQs to decay. And the different LCQs can decay on quantitatively different timescales. So here are some references. Maybe I will tell that the first one is actually a description of the algorithm that is used to search for these local and quasi-local LCQs. but I didn't have time to talk about it today. The second paper is about what happens when we perturb the Hamiltonian, and the third paper deals with the theory of spectral functions. So that's all I had for today, and thank you for your attention.
Thank you very much for your presentation. It was very insightful, but I think there is a lot to digest here. So maybe we have some questions from the jury.
I have one question that I would like to ask.
Sure.
So the first question concerns real materials. So can you say something about real materials that can be modeled with the use of this XXZ or XXX or those types of models? Do you have some materials in mind or some physical systems in mind here?
Well, basically the Heisenberg model can be used to study the quantum mechanical model of magnetism in materials, but to be honest, I haven't really investigated like the real world materials that correspond to, say, these concrete systems. But probably to study real world materials, we need to have a bit more complicated. We add some another terms, because surely there is no real world system that is completely integrable in the quantum sense.
Mm-hmm.
But these are just like, I think, idealizations of these models. But that's why we study what happens under small perturbations, because we probably can approximate real world materials models by adding perturbations to the simpler integrable Hamiltonians, and we would like to know what happens with the LCQs that we study. But I cannot give you a concrete example of this.
Mm-hmm. Mm-hmm.
But
in general, magnetism is this phenomena that is interesting.
Yeah, it's mostly magnetism, I guess.
Mm-hmm. And I have one more. Do you incorporate a temperature in those considerations, and in what way? So how would increased temperature affect those results that you have been showing?
So far, we haven't taken temperature in a way into account, because these are quite new studies, and we are making first steps into investigating the decay of these LCQs.
Mm-hmm.
And we're trying to start simple, because, well, we stepping in the dark right now, to be honest.
Yes, of course. Okay, so that's the plan.
That's just the first step,
for the future, maybe.
Yeah, possibly in future studies we'll try to incorporate this in our investigations.
Okay, thank you very much.
Thank you for a question. And now we have one question from our YouTube audience. A question from Alexander Kaczmarek. Are there any global conserved quantities? And if so, are they important for determining the stiffness?
Yeah, about say global conserved quantity, we can take, for example, a projection operator on Hamiltonian eigenstate would be global conserved quantities, because it obviously commutes with the Hamiltonian and it's highly non-local. However, it is not important for determining the stiffness, because, as I said here, this projection on the conserved quantities in thermodynamic limit vanishes for all non-local conserved quantities. So in thermodynamic limit, that means in like real world systems, they are not important. We care only about local and the more complicated quasi-local conserved quantities.
Okay, so once again, thank you very much for your presentation, and that would conclude our second and last theoretical session. But our program for the conference is not over yet. So after, I would say, a long coffee break, I warmly invite everyone to join in for our keynote speaker, Mykola Maximenko, who will give us a talk about using statistical physics insights in machine learning. So once again, thank you very much to all the speakers for insightful presentations, and for the audience for tuning in and watching the conference. Thank you, and see you during the keynote speaker talk.
Okay, so welcome after the coffee break, and now we will start with a presentation from our partner, SoftServe. Our guest is Mykola Maksimienko. He's the Research and Development Director at SoftServe, where he drives technological development and research in applied science and AI, human-computer interaction, and sensing. Mykola holds a PhD in theoretical physics, and his academic research experience includes a number of graduate internships and at the universities of Magdeburg and Göttingen, funded by German funding bodies such as DAAD, and DPG, with further postdoctoral research at the Max Planck Institute for the Physics of Complex Systems and Weizmann Institute of Science. And his presentation will be about physics-inspired methods for efficient training of neural networks. So welcome, Professor, and the floor is yours.
Thank you, Jakub. So I'm Director of Research and Development at SoftServe, not really a professor, but I'm also invited lecturer to a number of universities. And I'm very glad actually having this talk today at your conference, particularly in the spirit that this conference is very much physics related, so it's different applications of theoretical physics in complex systems, in machine learning, in non-equilibrium dynamics. So it's I'm very glad actually to be present in this conference and inspire probably you to work in very rapid direction of machine learning for physics and physics for machine learning. And actually today my talk will be covering two projects that I did together with my team at SoftServe and also with collaborators outside SoftServe. Let me very briefly actually recap why I'm focusing actually on the physics applications. So while being at Weizmann Institute and NPI for physics of complex systems, I was working actually on the quantum many-body systems and non-equilibrium dynamics of complex systems. And this actually drove me to a very interesting direction of statistical physics of machine learning, which I already started while working at Weizmann. And then actually while working in industry, I found several interesting applications, which I will be talking to you in a moment. But before I actually dive into the problem, I actually wanted also to give you a little bit of outlook. What is SoftServe? Why we are actually sponsoring this event, and we're interested to connect with you. So we are a large technology development and consulting company. We are more than 10,000 employees worldwide. We have several offices around Poland as well. So particularly our headquarters in Poland is in Wrocław. And at R&D at SoftServe, we actually doing both fundamental and applied research in a number of directions, which you might be interested in. So these are human-computer interactions. So we are developing new type of machine and interfaces to for the human to interact with the digital content. For example, on this image, you see a virtual hologram, which you might visualize in multiple ways. But together with our partners, we're currently working on the ways to touch these holograms, to use them to change your emotions, and so on. We also work deeply on the machine perception and ambient intelligence to design sensors and sensing devices to actually sense humans in some environments, and also for machines to understand where they are. And finally, we're actually focusing very much on the applied science and life science domain and in the quantum computing. So we have a small team, around 10 people already working in quantum computing. And as this is very much the scope of this conference, I'm also very much inviting you to look what kind of opportunities we have, and feel free to reach out to me, because not all of them actually are advertised on the website. So some of them are ad hoc. We reach out to some research teams for good input students or for great research scientists. So feel free to reach out to us. So now I'm switching on to the topic of this particular conversation. So I will be talking about machine learning and physics. And before actually diving into more details, I wanted to just set the ground for all of us. So what is machine learning, what I understand under this, and what kind of problems we will solve today. And Generally, we're talking about models which getting some data can define and some objective for what kind of prediction this model should do, can actually learn on this data and after some time start to predict correct results on the new data. And if that's kind of problems that we might have, it comes from the fact that actually this model, while the training, the objective is actually some complex function. And you can imagine this as being some valleys and mountains in this really nice landscape on the background. And our goal here, similar to physics, where we usually look for the ground states of some systems, and particularly if you're talking about some condensed matter physics problems, usually we deal with these very complex energy functions and energy landscapes, which we need to minimize. So this is very similar in machine learning. So here, we actually need to find minimas, some values of our cost functions in this sense, which actually leads us to the best possible generalization ability of our model, such that the model, if it receives the new data, it will actually perform well. So usually the models for this, they have a number of hyperparameters like learning rate, how quickly the model learns, like some parameters like dropout, number of layers in neural networks, and so on. All of these parameters, they actually are increasing the complexity of our training because we need not only actually tune the model parameters, we also need to tune all these hyperparameters. And for different hyperparameters, we actually can explore either some top of these mountains or we can actually dive deeper. So our goal is actually to go deeper. And today in this talk, I will outline two projects which are related to application of physics intuition to machine learning and to make this machine learning better, to find these minimas much faster and in a more efficient way. So one approach is to use so-called path-based optimization for the hyperparameters. So instead of choosing a single hyperparameter or set of hyperparameters, we actually allow these hyperparameters to change over the time as we learn. Or when we actually want to do some special prediction. And this actually allows us to avoid some walls in this landscape. So instead of actually going straight with the training, we actually can get some more interesting paths in the hyperparameter space. And this work actually was done in the collaboration with Vlad Pushkarev and Jonathan Efroni from the University of Technion, and Maciej Koch-Janusz, who were at that moment at the University of Zurich. Now he is in the University of Chicago. And by the way, Maciej is also from Wrocław, so that's how this talk is connected to Wrocław in some sense. And I also wanted to highlight another project that we'll be discussing today, is using the same kind of intuition to train binarized neural networks. So recently we actually presented this on the conference CVPR. That's a large computer vision conference on the workshop for binary neural networks. And this is a new approach which allows us to train binarized neural networks directly on the hardware device, which is a very tough and important problem in the space of tiny ML applications. So binarized neural networks, they are interesting in the way that here you cannot define gradients that easily. So that's why you need do kind of parallel training of the full precision model and the binarized model and store all those parameters in the memory, and that's a large memory footprint. So we, in this problem, we actually will propose the way that you can do this by introducing so-called Monte Carlo update rules that you can step from one configuration to another without actually computing for any gradients. So let's go to the next part of this talk. So the outline will be the following. So first, I will give you a little bit of outline, high-level introduction of why physics is so important in machine learning and why you should start thinking about this. And this is both in the sense of statistical physics and statistical mechanics in machine learning, but also for the new field of quantum machine learning, which we also explore in our team. And then I will get back to the deep learning and recap what is the deep learning, how actually we can use some tips and tricks to train those models and why it's important to use those tips and tricks. And then I will introduce this concept of diffusion for the training and why both phenomena are very much similar. And then introduce our path-based optimization and highlight how it works. Finally, I will also touch on the binary neural networks training, highlighting how similar kind of intuition could lead us to a new type of algorithms, which can be applicable to a new type of model. So let's start. First, I want to highlight that the applications of physics in machine learning are not new. So people actually were starting using this analogy and intuition way ago, like perhaps sometime in 80s or even 70s. While recently it's kind of a second wave or third wave of this interest of application of physics to machine learning, mainly because all of, not all, but many of the machine learning applications that we see today are kind of a black box application. When we actually have some model, it performs some task, but it's hardly interpretable. So, and there is still lack of understanding why these models actually learn well, and very much the process of training machine learning models relies on empirical trials and errors rather than deep understanding why this or that hyperparameter setting is actually good. So, and physics here is actually physics approach is very beneficial. So physics allows us to introduce a number of formalisms that are very well developed over recent years, recent century, I would say. And moreover, like the concepts like energy or noise or diffusion. On the other hand, various concepts and ideas which we used very well in the systems like spin glass or quantum system training, like tensor networks, actually could have a new wave by application then to machine learning. And particularly because some of these systems are very complex, physicists spent a lot of time to deeply understand these systems and develop the very well and detailed mathematical formalisms. So now we can use all of this work and apply them to machine learning. So this is a short intro, and now I'm actually going to machine learning, in particular deep learning, which is like the recent most hyped part of this field, and where I actually will introduce a few cases where physics actually provides really good intuition what's happening. So first of all, we all know that a lot of applications around us very much rely on the machine learning and deep learning, starting from this beautiful self-driving car experience that we have right now already in a number of cars, ending up to basic facial identification on the mobile phones. And the underlying systems that work for these models actually are majorly neural networks, which are highly complex models, which have a lot of hyperparameters and parameters, internal parameters, and allow us to predict, to train first on the large amount of data, and then to predict various properties on the new data. And on this very basic example that I have on this image is one layer perceptron, where I have, it's even not a convolutional neural network, but anyway, it's very simple to understand. So we have here input data encoded from X to Xn, which then is fed through this network, which is on a single layer. And here on each layer, I sum over input data from the input layer and with some weight parameters. So these weights are trainable. Plus I have some bias parameter, which also is trainable, so I can change it over time to achieve better performance of my model. And finally, this perceptron actually predicts some value, again, via applying some nonlinearity xi here. And And the training of these models is actually done in a very simple way using so-called stochastic gradient descent, where we actually compute the gradients on each step of our training and shift our parameters towards actually minimizing of an energy. So why it works actually is it's very interesting, because this model was introduced almost 50 years ago. So nothing new over the last 10 years or more. But currently we see a huge progress. And when the model was introduced, there were hopes that this will work because of the number of really powerful theorems. First was Kolmogorov-Arnold representation theorem, which stated that the complex functions could actually be represented as a number of more simple single argument functions. So we could represent a complex multiple argument function with kind of a sum of these neurons functions. And the second theorem, which actually also provided us hope, is that there is a universal approximation theorem that states that if you have an infinitely long, even a single layer neural network, it actually can approximate any function. So this gave us a hope, but it took almost 40 years to adopt these systems in practice. First was actually to select the right algorithms to train this. And finally, we needed also powerful computers, a lot of data, as we've seen over the last years, and a number of tricks. And apparently these tricks were like, instead of taking the whole data, we took a batch of this data. Instead of taking the perfect neural network, we actually applied so-called dropout rule, where we randomly kicked out some of the weights in the network over the training, and so on and so forth. And apparently, if you analyze all these methods in more details, you see that these actually are very much methods which introduce noise to the system. So instead of taking perfect system, you actually have a bunch of noise tricks. And all of them play so-called a role of regularization in the model. So you actually kind of prevent model to immediately stuck in some local minimum while training, because gradient descent is actually known to be very fragile towards local minimas, and these systems are full of local minimas. So they have the landscape which is super complex, non-convex, and actually it's very easy to stuck in some local part of the space. And hence these noise tricks actually allow us to train this model better. And the simple intuition, because the intuition for these noise tricks is very visible on this image. So imagine that you have a couple of minimas which are kind of equally good in terms of energy, but one of the minima is actually sharp, another minima is white. So if we train the model and end up actually in this minima, small deviations which actually happen because testing data is obviously slightly different than trained data. So small deviations could actually lead us to completely wrong and high cost functions. So imagine that we actually ended up somewhere here in the parameters space. So the same point for the testing function is actually very high. However, if you would apply some noise, you would kind of get out of the sharp minima, because for noise we always have small deviations, and we would actually train our model to end up in some more shallow minima. And for shallow minima, even if you actually are slightly apart, away from your perfect destination, on your test function, you still will perform well. So it's very important in machine learning, unlike in physics story. So you have two data sets usually. So you have training and testing. So it's very important not only perform well and find the best optimum for the training function, it's also important to be good on the testing. And that's where noise actually provides huge benefits for generalization of this model. And it's important also to state that this picture is super simplified. It's in real life, for the complex neural networks, it does not hold. And it does not hold for the simple reason. Our space of function that we want to minimize is incredibly high dimensional. So in that sense, the likeliness of actually ending up in some local minima is very small. Unlike we have actually a lot of saddle points, the reason for this is because you have so many parameters to have a true local minima, you actually need all the derivatives going to zero in that point. And that's unlikely if you have a number of parameters go more than 10,000 and more, or several millions of parameters. So the bigger your neural network is, the less is the probability of actually being trapped in the local minima, but more likely you will end up in some saddle point. And from that saddle point, if you apply a small noise, you always have a probability actually to go out easily. Moreover, there was a really nice paper actually from Jan LeCun's group, which showcased that if you actually increase the number of parameters in your system and end up in the true local minima, it's actually good for your training, because apparently the true local minimas are actually very low in energy, and most of them actually are very close to proper generalization minimas. So this is just an intro why it's important to add noise to your system, and why various hyperparameters that currently are being used actually control the level of that noise. And now let's step a little bit aside from that and try to think about this as a physicist. And apparently, if you think about training neural networks or any other machine learning model using gradient descent, is the same equation as Langevin equation, which is an equation of diffusion. So imagine having a molecule traveling in some environment, and if you increase the temperature, the stochasticity of this movement of this molecule will increase, and the molecule will have more energy, and it actually will travel faster through some environment. While if the temperature is small, the movements of these molecules will actually be much slower. So it's very similar to what we have here, while instead of a molecule or small particle, you actually have your model, your machine learning model, which lives in some hyperspace. And here we actually studying the traveling of the model in this hyperspace such that it minimizes the energy, in the way that we actually want to take gradient over the energy, and here this term actually adds some stochasticity or noise, or we can actually treat it also as a temperature. So how it works if you apply this intuition now to machine learning? So first you start from some energy landscape, and think about this as if you have a low energy. So your particle, this is your model, which actually travels in this landscape. It's important that this landscape is very high dimensional. So if your temperature is small and the energy of this particle is small, so then actually this particle cannot actually penetrate some high walls which you can encounter in this landscape. However, if you increase the temperature, what will happen that the particle will be able to actually go out of some local minima, but on the level of a landscape, it will look like the landscape became more smoother. So if just to look at this again, so here we had like more of a sharp landscape, but if you start to increase the noise or increase the temperature, the landscape becomes more smoother, until for very high temperatures, it's almost flat, such that our particle could travel anywhere it wants. And this is very nice analogy, and we used this to define a new kind of algorithm, which can be used in practice for training neural networks particularly very complex neural networks where you actually can need to find the right hyperparameter set. This is a complex problem in various production environments where it actually can spend several weeks just to find the right sweet spot of your hyperparameters. So here we use this path-based intuition. And the idea is that using this diffusion arguments, we actually look at the number of hyperparameters and analyze them from the diffusion point of view. Apparently, we can quantify how large is diffusion by analyzing the distance between two vectors as the model trains. So imagine that you start with this initial configuration and then you move to some other configuration. So these two are defined by some vector of your weights, and you can just compute the projection of one vector and the another and compute the distance. And if you actually look at this, we see that a number of hyperparameters indeed work as adding noise and temperature. So by increasing, for example, the randomness in your system, you see that your diffusion actually starts to grow as you increase more and more your hyperparameters. And you can actually define the number of these hyperparameters like dropout or learning rate, which is apparently also mapped to stochasticity, which actually satisfy this rule and work very well. While some other hyperparameters are slightly different, they might not necessarily satisfy it. So we need slightly different logic there, but still it's possible to train there. And having those, we actually will define a new type of algorithm. But before I go there, I will just remind how it's being done right now in many situations. So one case is very, very naive training. So we take a number of models with different hyperparameter sets, like this one, this one, this one, and just sequentially start to train them. So we train this model, we obtain the results, we see that it doesn't work. We change slightly the hyperparameters, this square here around. We train the model again, we get some slightly better result. Okay, we know where the direction is to move. We train further, and after some time, such sequential approach would actually lead us to some good hyperparameter set. Maybe not the best, but at least some hyperparameter set. On the other hand, this is certainly not optimal. It takes really long time, and it actually is still limited to a single set of parameters. So you just have a point. Another case is if you are actually available to access a large cluster of GPU machines and train multiple models in parallel. So in that case, you can just run a lot of same simulations in parallel, and such models would actually result in in almost the same results, but it will be done in parallel way. Then if you even on this step you don't have proper result, you actually can adjust them in the way that using some Bayesian rules, for example, and actually train once again with a second round until you find the right hyperparameter set on one node. And again, this is limited because at the end you will get a single point. So it's kind of it's so-called adaptive grid search or some parallel grid search. So there are many methods in the same spirit, but more or less the idea is very similar. While we propose slightly different approach, and apparently this approach was also investigated in a different way without physics intuition, also in the DeepMind group a few years back. And the approach was what would happen if we train not only weights, but as we train our model, we also are allowed to adjust the hyperparameters or in the same routine, actually at the same moment. And DeepMind introduced so-called population-based training, which is based on the greedy approach. The greedy in the sense that you have a multiple copies of your system, and you train them in parallel. But at some point, you actually allowed to compare them, and if some model performs worse than another, you can actually kill the worst performing one and slightly adjust the parameters of better performing, or copy parameters from better performing to a worse one, and train them in parallel now again. So in that sense, you kind of exploit a single tree which performs well. And you end up with very interesting pictures while you train. You see, you kind of start with multiple points, but as you train, you more and more exploit some particular trees which actually have the best performing models. And you can apply it for this method for a number of production level problems. Like, for example, in this case, you see it being applied to GANs, generative adversarial networks, to transformers. These are large language models. A3C. These are large reinforcement learning models, and so on. And you see that everywhere where you apply this method, you actually gain better results. So this is great, but as I said, that this method still has some limitations. So it very much depends on initial conditions. So as you start training, you actually select some random initial conditions. And then these trajectories are actually rooted and very much local. They actually start from some initial condition. And moreover, you actually discard a lot of information as you train. You kill all those worst performing replicas, exploiting only those which perform good. And that there is no guarantee that it actually will perform good, and you will not need to run everything from the scratch again. So we propose slightly different way, inspired by methods which actually are massively used in statistical physics, and these are used exploiting this noise-like property, as I said. So first we need to think about the hyperparameters, not just like as some hyperparameter which you can randomly adjust some number, but let's think about them as parameters which actually change the amount of noise in the system. So as you see in this image, you can have independent copies of your system, but for different level of noise. And this different level of noise kind of flatten your energy function. So now what we do, we allow so-called reversible jumps between these replicas. So our model can train with a single set of parameters, but then at some point in time, jump to another replica and exchange. But these are not done in the greedy manner, such that we discard the bad replica completely. We actually do it in so-called reversible manner. So we always have a probability of a particle to go to some lower temperature, and then actually heat again to a higher temperature, and do this in the reversible manner. So this actually guarantees. There are actually theorems in this Monte Carlo approach, which actually guarantees that these rules, these detailed balance rules, actually allow you to explore all the space of your hyperparameters in the correct way, such that you're not stuck in some particular part of your space, and you are not that much dependent on the initial parameters that you start from, because as you explore the space, you actually find the right part of your hyperspace where the model trains well. So technically, it's done by having actually multiple GPUs, and as you train your model on different GPUs, you allow different models to exchange hyperparameters. So I have some pseudocode here, but I will probably skip diving in more details here that much. So we end up, so here are a few examples of this training. So we end up actually having much better results for various models. So here are small experiments, but we also run it on larger experiments like ResNet, where our training actually gains a few percent of accuracy. And what is interesting that you end up having not a single parameter that you select, but as you train this model, you can actually reproduce this training without all those replicas further, where you just take your single replica and train it and over time, you actually change your hyperparameters in some very specific manner like this. So you kind of have a path in your hyperparameter space instead of a single point. And again, like for ResNet, this is an image for ResNet, you see that actually these methods provide you slightly better performance than training in other methods. So this is the first part of my talk. I will very much encourage you to take a look to this archive. We actually presented it in NeurIPS in 2019, so 9 missing here. And now I will move to a second part, but maybe there are any questions so far. Jakub?
I don't see any questions on the chat, but I have one question myself because you talked about that you had hyperparameters that were changing over the time in one of your works, and I was curious why is this noise classifier? How is this noise classifier different than like basic soft voting classifier? I mean the classifying of the adjusting of hyperparameters in your approach.
Yeah, soft voting, if I'm not mistaken, the method, it's very much kind of Bayesian optimization. When you, let me just go to this space here. I think you mean like when you have a picture like this, like you have several replicas, and then at some point in time you actually adjust your hyperparameters, right?
Yes. Yes. I mean, in soft voting, you have like a bunch of classifiers that have given tasks, like different types, like support vector machines, classification trees, etc. And then they are given weights to their answers based on their effectiveness. So if the classifier is effective, he has like a greater vote than a worse classifier.
Yeah. So in principle, this is similar in nature to what I called here like adaptive search algorithms. So you end up having still a single point in your hyperparameter space at the end, which turns out to be providing the best result. While these methods usually do not exploit the fact that you can actually adjust your hyperparameters over the course of training. Like you can go down, up again, and so on. So for example, in the sense, in our case, when I was presenting this, so in our case, this is a learning rate. So this learning rate should not necessarily always be annulled and reduced in time, but actually it can go be reduced, but then at some point we can increase it again to avoid some parts in our hyperparameter space where actually the model can stuck. But yeah, so it's important to actually take into account all those other methods and understand if they train better or not. But so far, we see that in our experiments, and also in this population-based training that I showcased, it's clear that you can achieve better results with this path-based optimization rather than selecting a single point in the hyperparameter space.
Okay, so but that was the one question. So I don't see any questions in the audience, so you can continue.
Okay, thank you very much. And all right, let's go further. So this will be a bit shorter story. I don't want to make another large seminar here on this, but it contains very much similar intuition. So for the previous model, we used Monte Carlo updates to actually exchange models which train in parallel. So we used stochastic gradient descent for each replica, but we exchanged the models using Monte Carlo rules. And then by having this Monte Carlo worked so well here in that method, we also thought that it's possible to apply it to different kind of models, particularly in the spirit of this similarity that actually Langevin equation can be trained with a standard Monte Carlo routine. And we applied it to the problem of binary neural networks training. So this is a very hot topic right now, particularly in the context of so-called tiny ML applications, where you want your machine learning models to be run on the edge devices and trained on the edge devices. So imagine here that you have actually some smart speaker at your home, that you want it to analyze your language, but you don't want this data to be transferred somewhere to the server. Or you want augmented reality applications, which actually need to be optimized for the speed such that its computer vision applications could actually very fast recognize the space you are in, or various sensing applications in automotive industry. So there are plenty of use cases, from personalization to security and various energy saving applications, where you actually want to have your machine learning models being on the edge. And moreover, they need to be optimized for energy and memory efficiency. And this is hard, because if you want to actually retrain your model, that takes a lot of effort in the form the only compute effort that you need to do, but also in terms of memory requirements. So during the standard training of your machine learning models, you usually need to compute gradients, and these gradients actually have a huge memory footprint, which at the end could be not applicable for edge devices, where you have usually very tiny amount of memory. So here is a really nice table actually from a recent paper, which also proposed different method to reduce this memory footprint. So in our method that we propose, we actually get rid of gradients at all. So we don't compute gradients. We actually use a fine-tuned Monte Carlo update rule to go from configuration to the configuration. And the idea why it is so came from the similarity of the binary networks to so-called spin glass models, Eigen spin glass models. So for those who are familiar with Eigen models, you know that this is the model of spins, which are binary variables, 0 or 1, up or down, and they can live on some grid. And this grid could be like square lattice, or this could be some random graph. And then the random graph could actually have a lot of frustration, because sometimes you could have some triangles that you need to optimize for, and you cannot optimize energy without actually degeneracy. So it introduces a lot of complexity here. So at the end, the optimizing energy in the spin glass model is a very complex problem, and people struggle a lot when they need to do numerical simulations for this model. And the standard approach here is a combination of various Monte Carlo techniques, and particularly using Metropolis Hastings Monte Carlo, which allows you to do reversible jumps from a configuration to a configuration. And moreover, people also apply this parallel tempering, replica exchange on top of that to avoid large walls in the hyperparameter space. But we applied this first step, where we actually train the model and go from one binary configuration to another using Metropolis Hastings update rule. And here, the difference between machine learning and Eigen model is actually quite drastic. On one hand, you have the similarity that your parameters actually are binary. On the other hand, you end up having very much non-local energy rules. So in the Eigen model, your energy is usually local. So if you have only nearest neighbor or next nearest neighbor interaction, you can actually localize the impact you have by flipping some spin in the model. While in machine learning, you first, let me just showcase it, you first actually flip some weight, and only then you compute the energy by actually passing through the whole network. And the energy is very non-local in that way. So you don't have this local tricks that you can use for spin glass. So in that case, we actually introduced, I will not dive too much in details, but I will just showcase the results. In that case, we actually introduced very interesting cluster-based rules, which are based on the intuition we gained from machine learning. Like we analyzed how the gradients form the clusters and how we can actually transform those into rules, which ways we want to update. And we showcase that this method is more efficient in terms of memory. It actually needs much less memory to store data, and it's comparable in the resulting accuracies to standard methods which are used right now using gradients like binary connect. And let me just maybe jump into those results. So first I want to just showcase that if you use no clustering, we already have good results which are comparable to binary connect. You see like 88% versus 90 or 93% versus 95, which actually are good results. Despite these are not like 100% accuracy, but still, if you quantize your model, you actually get a reducement in your accuracy. So it's good. It's comparable to what we have on the market right now. And when we started doing experiments with clusters of weights, we also noted that we can get better results. And moreover, if you start from a particular pre-trained model, imagine that you have a case where you train some model, you put it on the device, and then you want to train it locally in the online manner. Like if you have new person coming in the room, you want to recognize that person. So you already have a model, you just need to adjust your parameters slightly. So we actually noted that for such up-training, our model actually performs even better. So if it has already structure to pick the clustering from, so it actually performs better. So these are brief results. This is work in progress. We just presented it on the one workshop, and we'll put it actually on archive. And we still continue working in this space, analyzing new possibilities to improve this model. But very briefly, actually, I wanted to highlight the computational complexity and memory footprint. So instead of running the full backpropagation in like competitive methods are doing, so we actually get rid of that completely. So we just need to do twice binary forward propagation, which is much lighter operation. And also in terms of memory complexity, such network has actually benefits. It again does not need to store all those gradients in memory. So this was all that I wanted to talk about binary network. And I will be very glad to discuss with you further. And I'll let you with this last slide again about soft-serve, about what we do in different contexts, about human-computer interaction, machine perception, quantum computing, if you are wishing actually to go into that direction. So we are hiring right now. You can always actually reach out to me directly on LinkedIn, or actually go to our career website where a lot of vacancies are. So thank you very much. And I'm looking forward to actually answer your questions.
Thank you for your presentation. I will look at chat if we have any questions, but I don't see any.
Sunday evening.
Yes, Sunday evening, and we have more physicists on the audience and data analysts and like people that are into neural networks.
Yeah, I actually wanted to highlight that this field is filled with physicists. So in our team, we have quite many PhDs in physics.
as a software developer in my team, I have a guy that was a PhD at chemistry, actually. So there are many different people in different.
Great.
But I have a question,
Okay.
actually. So I was wondering if there are like use cases where you can't use the Monte Carlo approach and you must stick to the to calculation of gradients.
Particularly for binary network, I would say yes. So right now, it's slightly different. Like I would say, approach this question slightly from different point. So there are no widely adopted methods to train binary networks directly on the edge. So most of the methods right now struggle from one problem or another. So as I said, like we currently get rid of gradients at all. So this allows us, for example, to transfer this methods to run on FPGA, for example, where we actually quite limited in memory. On the other hand, our approach requires much more steps being done in order to achieve the right result. So there is a trade-off. You actually get a better memory complexity, but you need to do more steps in order to actually achieve the right result. It still takes you not that much energy to make a single step of your update, but it may take you longer. So that's what we work right now at the moment. So we want to actually improve our method in order to propose the next steps, not in the random fashion or some random cluster fashion, but more actually getting the some heuristic from how actually gradient descent works.
And is there already some hardware that like FPGA or something that already can use this method more effectively than like for example basic GPUs, or have you prepared something like this, or is it still work in progress?
This is still work in progress. That's a good question. So right now this is a proposed method. We developed, it's only developed in Python, not really optimized. But we, as a next step, once we will prove all the hypotheses, we actually will go implementing that in hardware. So right now we already can implement some version in hardware to showcase that it works, but it hasn't been done yet.
Okay. So that's all that I wanted to ask. I still don't see any questions. So thank you for your presentations and for your presentation.
Thank you.
It was a pleasure to meet you, and I will end the stream now. And I would like for anyone who was participating in this event or watching us on YouTube or Twitch to invite you tomorrow. We are starting at 12 a.m. In my time zone, GMT +2, and our guest will be Igor Sokolov. So thank you for today. And
thank you.
Have a great evening.
Have a great end of the weekend. Bye-bye.
Bye.